In this lecture, we're going to talk about something called the octahedral shear stress. Now, from a practical point of view, not very many people really use the octahedral shear stress, at least is in that form of the octahedral shear stress. It is related to the von Mises stress, and we'll see then therefore it's related to J2, second invariant of the Evdoric stress tensor. It is then therefore related to being a yield criterion for polycrystalline metals. That said, like I said, it's not a term that's used very often in practice, but it does have an interesting application to tie all these ideas together, including the idea of hydrostatic stress and so forth, not influencing initial yield for polycrystalline metals. It is a shear stress term. Ductile materials do tend to fail because of shearing stresses, so it kind of ties that into it that way. It's also a good application of tying together some of our ideas of principal stresses, directions, and resolving normal stress and shearing stress on particular planes. So from that point of view, I think this is a good lecture to go through so that we have a little bit deeper understanding of how all these things are tied together. First thing we need to understand about the octahedral shear stress is defined as something called the octahedral planes. And these planes are at direction cosines of 1 over square root of 3, 1 over square root of 3, 1 over square root of 3 from the principal planes, or the principal directions. So instead of having an arbitrary state of stress where we have shearing stresses and normal stresses, we're starting off with a very particular state of stress where we are already in the principal stress directions. And these principal stress directions form the basis of our coordinate system that we're going to use for this discussion. So this is a little more special than what we have done before. So for example, maybe the sigma p1 direction is the x direction, sigma p2 direction is the y direction, and the sigma p3 direction is the z direction. And I will draw the octahedral plane on these axes formed by those principal stress directions. Now, if the direction cosines have all equal terms, the intercepts on these axes will all be equidistant from the origin. And the octahedral plane then will be this triangular shape at an angle to the surface. And let me change this to dotted lines so that it looks like it's hidden. And maybe in red, I will show this unit normal bursting through in this direction. And these are the direction cosines, which can be interpreted based on the cosines of the angles from the x, y, and z directions alpha, beta, and gamma. So cosine alpha, cosine beta, and cosine gamma are all equal to 1 over the square root of 3. This is a unit vector. If we were to take n dotted with n, we would get 1/3 plus 1/3 plus 1/3, which is equal to 1. Square root of 1 is equal to 1. These are unit vectors. So we have everything going for us good so far in this picture. Now, it doesn't look like an octahedron. You may know that an octahedron is an 8-sided object. And I am going to attempt to draw an octahedron on the next page. The octahedron would be formed by a shape that looks like this in every quadrant as we go around the top and along the bottom. So we have, we'll end up with 4 of these triangles on the top coming to a vertex, and 4 on the bottom coming to another vertex. Let me give that a shot. Alright, like I said, it's a little bit hard for me to draw, but here is an octahedron. Now, these planes are supposed to be equal in size, and I don't think I've quite been able to demonstrate that. But I think you kind of get the idea. This is an 8-sided shape, and there's even, I've seen dice shaped like octahedrons, so that might give you another place to look for that. Now, we have a stress state formed by our principal stresses, and we want to resolve our traction vector to that particular stress state on that plane. We want to resolve that stress state to that plane to find the traction vector. Let's review what it takes to determine what a traction vector components will be given a stress state in a unit normal. So in general, our traction vector stress relationship in direct form looks like this. The traction vector would be equal to the stress tensor operating on a unit normal vector n. In terms of components, it would be something like Ti is equal to sigma ij nj. Now, we're in a very special coordinate system. One that is formed by our principal stress axes. So our sigma ij is going to look a little bit special. Our traction vector components T1, T2, and T3, the components of that vector would be equal to our sigma ij, that's our very special sigma ij, formed by the three principal stresses, sigma p1, sigma p2, and sigma p3, with zeros, because we don't have any shearing stress on our principal planes. And we have that very particular unit normal direction equal to 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. If we do these multiplications, it's pretty straightforward. The three traction vector components are the three respective principal stresses divided by the square root of 3. Okay, so what we've done is for our particular plane, taken our stress state and we've resolved it. We've determined the traction vector that's acting on this plane. Now, these traction vector components aren't necessarily lined up with the unit normal n. They'll only be lined up with the unit normal n if sigma p1, sigma p2, and sigma p3 are equal. So our unit normal might be coming off in this direction, but our traction vector could be maybe off in this direction. We want to do a couple things here. First, we're going to take and project the traction vector into the direction of our specific unit normal. And then we're going to do some vector manipulation to figure out the shearing stress that is acting on the octahedral plane. Right. First, let's find the normal stress that is acting on the octahedral plane. The way we find that is we project t in the direction of n. Basically what we're going to do is we're going to take t and dot it with our unit normal. Now our t, we just saw, were these respective principal stresses divided by the square root of 3. And our unit normal is 1 over the square root of 3. This produces a scalar value. And the scalar value then is equal to sigma p1 over 3 plus sigma p2 over 3 plus sigma p3 over 3. This ought to look kind of familiar based on what we talked about in the last lecture about hydrostatic stress. The trace of the stress tensor in any coordinate system is an invariant. This is I1. Sigma P1 plus sigma P2 plus sigma P3. 1/3 of I1 is the hydrostatic stress. Okay, so that in itself is kind of interesting. When we start off with our principal stress directions and we look at the octahedral plane, the plane that has the unit normal 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, the normal stress acting on the octahedral plane is the hydrostatic stress, P. Now, if we have a ductile material that fails or yields because of shearing stresses, we've already discussed how the hydrostatic stress doesn't influence the yielding behavior of most of our polycrystalline metals. So if we want to develop a yield criterion, it's not this component that we're interested in. What we're really interested in is the shear component. Let me project T into the direction of N. Let me use a different color. So maybe out in space, this is the projection in the direction. So if I take T dot N and multiply it by the unit normal N, it forms a vector in space that goes out in this direction. So this would be T dot N times the unit vector N. And if that doesn't cause yielding, well, maybe the rest of the stuff does. Maybe this part of the vector in our vector addition would cause yielding. So this would be the shear stress, and we're going to find this knowing that this is a right angle. We can use the Pythagorean theorem to look at the magnitude of the traction vector T. We're going to look at the magnitude of this red vector, and we're going to use that to find the magnitude of this black vector. So let me say that this is T. It's perpendicular to N. And let me call this one in red the portion of T that is parallel to N. Let me make a little bit of room. Alright, so I just move that diagram up a little bit. And just to make it clear, T dotted with N times N, T dotted with N is the hydrostatic stress, times by the vector N is P over the square root of 3, P over the square root of 3, P over the square root of 3. So that's T parallel to N. T itself is sigma P1 over the square root of 3, sigma P2 over the square root of 3, sigma P3 over the square root of 3. What I really want to find is I want to find the magnitude of T perpendicular to N. This is where the Pythagorean theorem comes in. The magnitude of T perpendicular to N squared plus magnitude of T parallel to N squared plus T perpendicular to N squared would be equal to the magnitude of T squared. What I really want is the magnitude of T perpendicular to N. So t perpendicular to n in magnitude is going to be equal to the square root of the magnitude of t squared minus the magnitude of t parallel to n squared. Alright, so we need to find these values. If I take t dotted with t, we know that it's the magnitude of t times the magnitude of t times the cosine of the angle in between, which is 1. So t dotted with t is equal to the magnitude of t squared. And let's see what we get. We would have sigma p1 squared over 3, sigma p2 squared over 3, sigma p3 squared over 3. So let's see, sigma p1 squared over 3 plus sigma p2 squared over 3 plus sigma p3 squared over 3. Alright, now let's take a look at t parallel to n. If we want the magnitude squared of t parallel to n, what we're going to do is we're going to take t dotted with n, that's a scalar, okay, so that'll be that squared, and then we'll have n dotted with n. And we can square that too. N dotted with n is 1, so this term, this magnitude, will be equal to 1. So we're going to focus on this first part, t dot n squared. Now for right now, I'm going to leave this as if it has components that are arbitrary for our unit normal vector. Right, so t dot n we would have our traction vector components t1, t2, and t3 dotted with n1, n2, and n3. And we had seen previously for our principal stresses, T1 was sigma P1 over the square root of 3, and sigma P2 over the square root of 3, and sigma P3 over the square root of 3. And then we dot it with our particular unit normal, 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. So T dot n is equal to 1/3 sigma P1 plus sigma P2 plus sigma P3. And then T dot n squared is equal to 1/9 sigma P1 plus sigma P2 plus sigma P3 quantity squared. So now we're in a position to be able to take and subtract those two terms from one another. It's going to be a little bit easier to work with this thing if we square it. And this thing on the left-hand side, that is our octahedral shearing stress. So this is tau octahedral squared. All right, so let's put some of these things in here. Tau octahedral squared is equal to the magnitude of t squared, which is a third, sigma p1 squared plus sigma p2 squared plus sigma p3 squared minus magnitude of t parallel to n squared, which we just said was 1/9, sigma p1 plus sigma p2 plus sigma p3, that quantity squared. Alright, next comes some algebra. We're going to square the second term out, and then we're going to do some rearranging. So I'm going to pause the video and write that down, and then we'll take a look at what we get. Alright, so we do some algebraic manipulations. We collect the principal stress terms squared, and we also collect common cross terms like sigma p2, sigma p1 plus sigma p1, sigma p2. That should be in there somewhere. Let me take a look, make sure I've got it. Like this term and this term are the same, so we're collecting them. I factored out a 1/9 from all the terms. So here I have a 3 sigma p1 squared, a 3 sigma p2 squared, a 3 sigma p3 squared, minus a sigma p1 squared, a sigma p2, and a sigma p3 squared, and then minus 2 of these cross terms, each pair like that. I've reduced the 3 sigma p1 and the minus sigma p1, both of those squared terms, down to 2 sigma p1 squared, and likewise for these others. I have the 1/9 out front. This factoring comes from sigma p1 minus sigma p2 quantity squared plus sigma p2 minus sigma p3 quantity squared plus sigma p3 minus sigma p1 quantity squared. And that should start to look familiar. Let me make a little bit of room on the next page. If we were to take and multiply and divide by 2, we would get sigma p1 minus sigma p2 quantity squared, sigma p2 minus sigma p3 quantity squared, and sigma p3 minus sigma p1 quantity squared. And this term is the von Mises stress squared. Now it's the principal stress form of the von Mises stress. So what we have then is tau octahedral squared is equal to 2/9 sigma von Mises squared, or if we take the square root of both sides, the octahedral shearing stress is the square root of 2/3 times the von Mises stress. And again, we can relate this to yielding. If the von Mises stress is equal to the yield stress, sigma naught, then the octahedral shearing stress is equal to square root of 2/3 times the yield stress at yield. Alright, so through these manipulations we've learned a couple things. We've seen how the octahedral shearing stress can be related to the von Mises stress. Talked about the octahedral planes and its significance. We've had a demonstration of using our traction vector stress relationship to find the traction vector components on a plane with a given unit normal. And then we've used the Pythagorean theorem to back out a shear stress magnitude using our vector algebra.